Let us have a simple example. Suppose that we have an AR random process, and suppose that the autocorrelation function Rxx of m is given, and we want to find the parameters of this AR process. So in this example, for simplicity, we assume that a very simple example, AR1, the simplest case. This is the case that your random process x of n can be calculated using this equation. In other words, x of n can be calculated as an uncorrelated white noise. This is a white noise, a stationary noise. That means that RVV of m is equal to sigma 2 v and then delta of m, and delta of m is equal to 1 if m is equal 0 and 0 otherwise. So this is delta Kronecker function, and then plus a1 x of n minus 1. AR1 means that to calculate these you need one previous sample, and then your previous sample linear combination, which is this one plus this one, gives you this. So this process has two parameters. Parameter 1 is a1, which is the coefficient, and the second parameter is sigma 2 v. We want to calculate them. What is this and what is this number, assuming that I have Rxx of 0, Rxx of 1, and etc. We have some autocorrelation coefficient and we want to calculate these parameters. So this is Yule-Walker equation that we got. So we have these two things. So the first step is that I can multiply these, both sides of this equation, by v of n. So I get x of n, v of n, let's say conjugate, minus a1 x of n minus 1 times v of n conjugate is equal to v of n conjugate. Now, you apply this expectation operator on both sides of this equation, and then expected value of these will give you expected value of x of n v of n conjugate minus this term, because this equation, this recursive equation, is causal, so the previous sample should be uncorrelated with this one, so this should be 0, minus this expected value of these is going to be equal to sigma 2 v. So from here, what I got is that the cross correlation of these two guys becomes this one. Now, I could multiply the same equation, this time by something different. I could multiply both sides by x of n, for instance, conjugate. So I get x of n conjugate minus a1 x of n minus 1 x of n conjugate equals to vn x of n conjugate. Or you could take a conjugate of everything. So in that case, these will be same because conjugate of these is equal to, and then you could put conjugate on this one and conjugate. So assume that for simplicity, everything is real, so you don't need to put conjugate. But if they're complex, you have to put the conjugate in. Now, you can take expected value of this one. So expected value of this one gives you this equation. Expected value of this gives you this one. And then you get this one. Expected value of this is equal to this because I already have calculated. So I get a first equation. Remember that I have two unknowns, a1 and sigma 2v. Using one equation, I cannot determine two unknowns. So I need another equation. So what I can do, I can get this equation again and multiply by x of n minus 1. So I get x of n times x of n minus 1 minus a1 x of n minus 1 x of n minus 1. So if they're complex, one of them should have conjugate. So you multiply it by x of n minus 1 conjugate, and then you get v of n x of n minus 1. If complex, you put a conjugate. And now you can take expected value. Expected value of this is 0 because this is a previous sample and this process is causal, so you get 0. And this one becomes Rx x of 0 and times A1, and then you get Rx x of 0 minus this. I'm sorry, this should be Rx x of 0, and this should be Rx x of 1. So you get this one is a second equation. So I use this green equation with these these two green equation, two unknowns, two parameters, and two set of linear equation, two linear equations, which we call a Yule-Walker equation. Two unknown parameters, we solve it, two equation, two unknowns, and then you get your parameters. By doing that, so these two equations, if we solve them, we can easily calculate, because from this equation you get A1. You could put this side, the other side, and divide both sides by Rx x of 0 is equal to Rx x of 1 divided by Rx x of 0. Now, if you put this R1 on the first equation, then you get sigma 2v. So both solutions. So you get two solutions. Two parameters are there. So you see that for AR random processes, AR1, calculation of unknown parameters in terms of Rx x of 0 and Rx x of 1 is very easy. So this is why there is lots of applications for assuming AR random processes. You can see that for moving average or ARMA random processes, solving this set of equations can be sometimes very expensive and not very straightforward, because the equations are not usually linear. But you always, for any AR, let's say here we are dealing with AR1, but if you deal with ARM, then you will have m plus 1 parameters, unknown parameters. But when you write this equation, you will again get a set of linear equation, and the solution is very easy.